Good afternoon, everyone. My name is Venkatesh Ramanathan. I work for PayPal as a data scientist. The topic of my talk today is on active learning for fraud prevention. So this is the agenda. I first introduce briefly about myself and what we do at PayPal. Then I'll introduce the fraud prevention currently in place. Then I'll talk about the algorithm, specifically on active learning, how it's going to help with the fraud prevention. I'll share some experimental design and some early results. It's a huge area, obviously. I still have a lot of experiments running to have conclusive evidence on active learning, but some initial results which are promising. And I'll conclude my talk on what my future work is going to be. I essentially was a software engineer for most part of my career. Then I was developing software for scalable backend software systems. I had a MapReduce-like framework even before MapReduce came into existence. And post Hadoop days, I built several scalable systems using Hadoop and HBase. Later part of my career, after I got my PhD in computer science, so it's mostly on the research side, primarily on the machine learning researcher. I have done research in various areas of machine learning, primarily on face recognition. I've done some research on phishing and email spam detection. And last 4 years, I've been at PayPal on fraud prevention. PayPal, briefly about PayPal, we process about, we operate one of the largest payment network. And we have processed about 5 billion transactions in a year, about, the slide is not clear, about 300 payments per second. On average, at peak, we process over the 3,000 payments per second. We keep all our customers' data secure, so we operate one of the largest private cloud in the world. We offer both buyer and seller protection, so customers have a very fair experience when they are using PayPal. We operate in over 200 countries. We have about more than 180 million active customers as of last quarter. One of the biggest strength for PayPal is state-of-the-art risk management systems, and I belong in that organization, which is primarily involved in reducing fraud and reducing payment loss. So how fraud prevention currently is done at PayPal? At a high level, we apply sophisticated machine learning statistical models. Our group is established more than 10 years back. We have a lot of proprietary algorithms in the early days, primarily on, largely based on neural network-based algorithms. Even before deep learning became the buzzword, we had neural network-based models for tackling fraud. We have other statistical models, including regression, logistic regression. We have a scalable multi-layer infrastructure software to help fight fraud. More importantly, we have a team of data scientists, a huge team of data scientists working on right from engineering sophisticated features to developing machine learning models to applying rule strategy for rule-based live invocation. We also have intelligent agents from both from financial and intelligent experts who are basically primarily helping us with the creation of intelligent features, which goes into our models. At a high level, we have a fraud prevention is three-tier architecture. So the transaction level, most of our fraud is handled at the transaction layer. Anytime a payment goes through, our model kicks in, gives a score based on the features. And that is the primary way to fight fraud. We apply a set of models at a real-time layer, and we also have a sophisticated layer for once the transaction is complete, we apply more sophisticated algorithms to reverse some of the transactions which we approved at a transaction stage. We also have account level layer. We build user profiles based on normal and abnormal activity. And whenever we detect any type of changes to user's profile, like they made some bunch of transactions and they suddenly updated their shipping address to ship to a different country, those kind of activities will trigger anomalous behavior in our system, so that we use that as a trigger also to fight fraud. We also have network level models where we monitor account transactions. Typical fraudsters, what they do is that they collect money from several accounts and funnel it to a handful of accounts. From there, they can withdraw the money. So we have network level models to tackle that kind of abusive behavior. So obviously, we all know fraudsters are becoming increasingly adaptive and smarter. We needed cost-effective solutions and scalable and computationally efficient prediction models. Our prediction models are, the current models is extremely superior. In fact, what we do is that we continuously challenge ourselves. Internally also, we challenge our vendors, outside vendors, to challenge our production models. We give our score and ask them to build models based on our data set. Currently, nobody is able to come close even 20 percentage points. That's because we have a matured fraud detection system. Largely, most of it is because of the intense feature engineering we have in place to detect all kinds of fraud patterns. What we have is that we have an internal challenger team to, most cases vendors fail to beat our models, so we have an internal challengers team to beat our models, because even a small percentage, you can see that this is the area under the ROC curve, plot of true positive rate versus false positive rate, close to 0.96 on a validation data set, which is really, really hard to get on payment fraud space. But still, we want to improve on this, because even a small percentage is a huge savings and loss for us. So our company invests a lot of money in building internal challenger models to challenge some of our champion models. So obviously, in order to build champion models, how can we build better models? We wanted to, we started about a year back to completely take a look at all aspects of our traditional model building. This is how traditionally machine learning models are built. You have a whole bunch of data set, and you have features, and typically it's a supervised learning case. You have a tag which says it's a fraud or not fraud. You have a training data set. You build a model based on that in an offline way and use that model to enforce fraud for a live invocation of that model. Obviously, we can expand on the what can we do? We can expand on the data set size. We have been already using big data scale our current model, so we can expand. Most of our models are years worth of data set. If we wanted to, we can expand to 4 or 5 years worth of data set. Obviously, our feature engineering is already robust. We can build a more robust feature engineering, whether that can help. Obviously, we can look at some of our algorithms. Our machine learning algorithms are proprietary neural network based algorithms. So we can take a different look at some of the machine learning algorithms. And the last one is obviously the label itself. All supervised learning algorithms makes a fundamental assumption that your label is accurate. So we can take a deeper look at are we labeling our transactions correctly to build our models. So this particular talk, we are doing on all those space, but this particular talk is primarily around the labeling stage, which is where active learning comes in. So the algorithm to tackle the labeling problem is active learning. I'll talk briefly about what active learning is. Obviously, supervised learning algorithms require the data to be labeled. Labeling is difficult, extremely time-consuming and expensive. Especially in fraud cases, like for example, labeling. So you can give an image. You give it to somebody, and you can say this is an image of a dog or a cat, right? It's easy for a human to label it. Fraud cases, it's not that easy. So it's extremely difficult for time consuming. Usually you need experts to label a fraud case. That's where active learning helps. So the fundamental idea behind active learning is that if you give to a machine learning algorithm data, it can choose the data from which it can train the model, then it typically it results in a better predictive performance. That's the idea, is that instead of just using all the data you have, just choose the data before you train a model on it. This is actually helps to overcome the labeling bottleneck, because that is one of the most expensive part of building machine learning model is the labeling part. So it's the way it works is actually it's an iterative approach. So you start with a small labeled data set. So from the small labeled data set, you build a mini model, sort of using whatever algorithm you have. Then use that model to make a prediction on a huge pool of unlabeled data set. And from the unlabeled data set, you apply some kind of strategy to find out which are the ones actually for human to take a deeper look at, whether to relabel it, those samples, right? So that human actually makes a determination. There are several strategies. I will go over different type of strategies of selecting what goes in actually selection of those data from the unlabeled data set. And you after the human labels it, you re-add that to the labeled data set and rebuild a model and iterate it until you get the enough predictive performance which you are looking for. So there is no actually stopping criteria. When you are happy with your model, you stop it. But it's typically an iterative technique. Keep doing that. There are three types of problem scenarios where active learning is applied. This is there is a very nice survey by Burr-Settles. Actually, I had the reference before. So you can look up for Burr-Settles. He has done extensive research on active learning. Three main problem scenarios are membership query synthesis, where you request labels. You have a pool of, you have a space of unlabeled data set. The membership query synthesis request labels for any of the data set without any criteria in mind. The stream-based selective sampling is selective sample set. So how we selectively samples is some kind of criteria it uses to selects it, and if it finds that there is no enough information in the sample, it discards it. So it's similar to membership query synthesis, but it just you try to membership query synthesis, you don't discard it. You just whatever sample you selected, you ask a human to label it, and that gets added back to the pool. In the pool-based sampling is more of it's a batch-based approach. So you have a pool of samples. In the stream-based, you have unlimited number of samples, and the acquisition of the unlabeled data itself is not considered or not expensive in that sense. In the pool-based sampling, you have a pool of unlabeled data set. From that, you select samples for a human to label it. So there are several sampling strategies. Actually, the most simplest one is something called uncertainty sampling. So if you think of it, is that you basically you have a labeled data. You have a model, and you have a huge pool of unlabeled data set. The uncertainty sampling is to ask that model to come up with a score for those unlabeled data set. So if the score is, let's say if it's a binary classification, 1 means fraud and 0 means not fraud. If it's something, the score is close to 1, obviously it's more like fraud, and if it's close to 0, it's not fraud. But if it's close to 0.5, that means it's not sure whether it's fraud or not. The model is not able to make a firm determination whether it's fraud or not. That is the kind of samples which you want to give it back to the human. Model is unable to make the firm determination whether it's fraud or not. Let's take a deeper look at that particular sample and ask the human to label it or discard it appropriately. So uncertainty sampling is the easiest way to understand active learning. And that is query by committee. In uncertainty sampling, you just use a single model to label it. In query by committee, you use a committee of models. It's like an ensemble of models. You have several models. It can be a combination of different algorithms. You come with the score for each one of them, and you select a sample which most models disagree on. Use that for the human to label it. And there are several other variations of it. Actually, most of these earlier ones are, in this figure, actually, if you look at it, the uncertain, this is actually representing a 3-class classifier. This is in the edges, that means that the labeling is pretty clear. You don't want that human to annotate that sample. But if it's in the middle, that means that's most uncertain about. That is actually the most informative sample for human to take a deeper look at for labeling. Actually, none of these ones are robust to outliers. For example, in this case, if you ask an uncertainty sampler, sampling strategy, which will look for anything close to 0.5. So if you look at it, this is a boundary separating this class and that class. It will pick this if you use uncertainty sampling. But this is actually an outlier. It's not actually neither belong to this or that. So the density weighted methods actually, sorry? Oh, sorry, I'm pointing, thank you. This is, if you look at the sample A, for example, this is in the middle. It's probability 0.5. Uncertainty sampling will select this, but density weighted methods take into account the distribution of these data set, because not only you want to discard the outlier, because all these are not outlier agnostic. So you want to pick a sample which also takes into account a sampling strategy which takes into account the outlier, selecting the samples. So those are all the primary sampling strategies. So essentially, active learning is selecting the best sampling strategy to give the samples, then let the human work on it rather than this thing. So this is actually a toy example. For example, this is a toy data of 400 instances. So decision boundary is what it separates this class from that class. So if you randomly pick 30 samples, for example, this particular model was built using a logistic regression using 30 samples. If you randomly pick a data, it results in 70% accuracy, and this is the decision boundary. Instead, you apply active learning. In that case, it results in 90% accuracy. So this is the proof that active learning, which samples closer to the boundary using uncertainty sampling, results in 20% improvement in performance. So that's the idea behind the active learning. I went through a little bit. The fraud case actually is that obviously data is unbalanced in the fraud case. So when you are sampling it, you have to make sure that the sampled population after when human labels it, we add that back to our labeled population to build the model. You want to make sure that that the proportion remains the same, because you don't want to build a model on a balanced data set, which will be totally useless when using for real fraud scoring. So you want to make sure that the proportion of the unbalanced nature is maintained. So that is something is specific to fraud or any unbalanced problem. So we want to take into consideration, which active learning doesn't, the generic active learning doesn't apply this particular case. The other thing is, obviously, I already told it can be require trained experts. You can use Amazon Turk, for example. In the Amazon Turk case, if you want to label an image, you can give an image to a whole bunch of crowdsourced people to label it. But in that case, even the abuse case can be tackled, because you can average out the prediction of the labeling of several users to rule out abuse cases. But we can't use that. Plus, we care about our users' data, so we can outsource it. So we have intelligent analysts looking at transactions to label it. It's time consuming, I already mentioned, and let's see. Fraud labeling also require more than just, so if you want to tackle transaction fraud, it is not enough you just look at just specific transactions. So our agents, analysts, they want to look at what happened before and what happened after, and also look at other pieces of information to solve the puzzle. So we need to, but the typical fraud transaction, active learning applies for you just take a single transaction, you just label just that. So that's not enough. Fraud labeling also require data from the entities, for example, other entities. So for example, obviously, when you're doing transaction fraud, you can look at all the transactions for that particular customer before and after, but you also want to look at has there been any other transactions from the same IP address. We also use some kind of signature-based way to match those transactions because fraudsters actually avoid the IP. They can sit behind a proxy, or you can store network to hide behind. So we don't know the true IP address. So we have a signature-based way to detect how this transaction is similar to that. So we not only take that particular transactions where the signature matches, we also take that part of the pool in creation of the final pool for the analyst to label it. And other than that, we also need to look at the aggregate data for fraud. Fraud tag matures at different points in time, which is obvious. So usually people file for chargeback much later in time, so you don't know whether it's fraudulent or not at the time of transaction. So this is actually at a high-level framework. So basically, the labeled we have a labeled data, and our models are actually for this particular work used a committee of deep learning based model and gradient boosted tree, some of the state-of-the-art machine learning algorithms out there. Build models using that to predict the unlabeled data set, and used query by committee, basically the score of these two models to determine whether that should be, we want the human annotator to label it. We also, just like I was saying, that we need to create the all the transaction frauds. We need a transaction to build the model, but we create the bags of the one I talked about creation of bags, which includes pre and post transactions, and also look at other fuzzy matching to determine all other transactions which should be part of the bags. We also, other thing is that because our models are really mature, it's really hard to get any type of performance. It's just not enough if you just give all this data to the user to label it. In most cases, we also need to think of near feature engineering. For example, if we say that, okay, if we find that, do we want to determine if these accounts are linked? So the linked account is kind of an attribute or a feature which let's say that's a new feature we come up with that we have been using for some time, but that's just an example I'm giving. Is the account linked is a new feature which, let's say, we come up with, and the analyst or the intelligent analyst come up with the new feature. And what we do is that because we need to build the models using past historical data, and those data doesn't have this new feature, we need to simulate those features for all the other transactions which we have. Based on the data set, based on the logic we come up with, we need to simulate features for the ones for which these feature doesn't exist anymore. So, our active learning is not just about the learning part. It's also, we spend a lot of time in active feature engineering to, because in most cases, even with the score of 0.5, we won't be able to figure out, the analyst won't be able to figure out why our model was not able to detect it. In most cases, we need newer features to make the final determination. So once we do all the stuff, then we also look at other social networking data to make that conclusion. Then those data gets added to the labeled data. Obviously, this is you can see that this is a pretty intensive effort. We typically we had to build a lot of tools to do some of this work for analysts easier. Previously, at some point, it used to take about 2-3 days for some of the transactions to be really sure. So it was down to an hour a day, and with this particular approach, we are able to reduce it about 30 minutes for particular transactions. So, but still, that is huge actually. So you can see that it's pretty expensive to label that. But we have a lot of analysts working on it. So this is briefly on the deep learning side. Is that 2 models were built using deep learning, and there are a lot of there was a previous work on me, but just to give you a brief introduction on deep learning, it's a network has many layers of nonlinearity, then it's deep. But obviously, deep learning requires lots of training data and scalable platform to be effective. Our earlier models are all neural network based, and that we extended this to deep learning based model. The network topology which was used was mainly feed-forward implementation. There are other variations of architecture, but that wasn't used for this particular work. The other algorithm is gradient boosting trees, which is also, we found it extremely effective in improving predictive power of some of our models. It's an ensemble tree-based algorithm. You build a tree in sequence. So you take a sample, you build a tree, and then the subsequent iterations focus on the ones where it made a mistake. It's an ensemble model in an iterative fashion. This also some of the with the deep learning based models, because you need to have a numerical features, so you need to have some kind of transformation on the raw data set to apply the deep learning based model. But gradient booster tree is very powerful in the sense that you can feed in the raw data, it is agnostic to any pre-processing technique. So it's also handle a mix of categorical and continuous data types, which makes it easier and quicker to you can build tree-based models quicker using GBT compared to deep learning. But deep learning captures most of the complex non-linearity. So we found that certain fraud patterns, complex fraud patterns, the deep learning model is able to detect better than GBT. So there is pros and cons with both of them. So we ended up using both. So I already went through all of this. So experiment actually it's training data for this particular work. I used 1 year's worth of data set. 11 million transactions is a very subset of our one of the specific type of fraud, which we wanted to see whether the active learning helps, and 1 million was used for active labeling. The test data is about 4 months and 4 million transactions. About 600 features were used for building the model. We have several open source implementation. We also have proprietary algorithms for this particular work. I used H2O, which is there are several talks. Actually, you should visit their booth. It's extremely very robust, scalable platform, and it's open source out there. So they have a lot of algorithms, including deep learning and GBT implemented. So if you haven't played with it, I strongly encourage you to look at H2O. We have found it our adoption internally of H2O tool. There are several tools, open source tools out there, TensorFlow and everything. But I found this one is that the interface is very simple, and the choice of R versus Python interfaces. So all this open source out there, so you try it, and it's not robust, and you end up spending time in debugging more than actually building models. We've been using H2O for more than 1.5 years. We found it extremely robust, and it's improved a lot, and the GPT implementation rocks, and they have a lot of new features. Most of those, if you look at their implementation, you look at the source code, most of their algorithms, they've taken some of the state-of-the-art implementation of regularization. Any of those algorithms out there, they have taken that and coded it. So I strongly encourage you to give it a try. Most of my work is using for most of the integration efforts, and also the there is an active learning package in R which is not scalable, but I implemented the scalable version of the sampling technique using Java, but R was used as a front-end interface to run through everything. So this is actually some of the early results. As you can see that a lot of time we ended up spending more time in building tools for our analysts to actually label it. So we didn't get much time to actually look, because you can see that the number of instances we used 1 million instances, but 1 million is nothing for us actually. We build models in hundreds of millions of samples. So we wanted to explore active learning on much bigger scale, and also we wanted to get much better performance than what we are getting. But we are getting, you can see that it is showing promise with 1 million instances. AUC was able to improve from 0.96 to 0.97, you will see that it's not that much, but it actually translates to huge savings in loss for us actually. But this is not the performance measure we use, but we can't disclose our internal benchmark, but it is showing a lot of promise. So I don't have much on the more on the results part, but so we to conclude, essentially deep learning GPT has shown tremendous performance for fraud detection. Each has its own pros and cons. We were GPT actually when we were able to deploy because of the lack of not needing to do the pre-processing, we can actually deploy it quicker, but deep learning requires a lot more rigorous work before actually we can deploy it. Active learning, we have shown promise with these early results, but we're still continuing. As I said, that it significantly reduced our labeling cost. We're down to about 30 minutes using active learning, but it does show promise for fraud prevention. That's all I have, and obviously more time. Any time for questions if you have any. Yep.
So the chart you were showing where zero samples of active learning has this performance, and then going up to 1 million is better. So at the 0 point, you already have lots of labeling from previous.
That's correct. Yeah, exactly.
So how much previous labeling was there before it happened?
Yeah, 10 million samples actually.
So there was already 10 million, and you're adding 1 million
more. Yes,
that's
correct. Yeah. But again, that's again a sample of our data set. We have kind of semi-automated way to, we don't have 100% manual because it would take too long to label it. Sure.
Support label later when you train with the model, when you make reason on the train model, and if it makes them, false negative or false positive.
Right.
And you human factor right there to improve that.
Yeah, absolutely. I cannot disclose those results for you. The AUC is the measure which we have an internal benchmark, our internal measure performance metric. We were able to improve our with basically keeping the false positive low still, but we were able to improve our internal benchmark. So yeah, AUC, yeah, you are right. I cannot, unfortunately, I cannot disclose that specific numbers to you. So. Yeah, there is actually some theoretical work which is being done in that. So there is, it's still in the research stage. So there is no way, no conclusive theoretical proof that this is how many samples you actually need, some kind of an upper bound on the thing. Beyond that, you won't get that. But they are still in the research stage. There is not much conclusive work on that. That's a good question.
So there's this back and forth where you've got active learning saying this is what you should label next, and then the labeling actually happens. Now the labeling actually happens fairly slowly, right?
Yes, exactly.
So is active learning saying, look, these are the million you have to do, and then waits and the million all get labeled, or is it back and forth where it says label this one next, now this one, and waits for the labeling?
Yeah, we have actually several agents looking at it. So it's not one. So in that way that. Oh, sorry. Actually, he was saying that labeler, active learning actually says these are the ones you should label it, and human looks at it, right? So the question was, is there a back and forth? Do we have to wait for the process to complete before we move on to the next one? Some part of it's parallel, can be parallelized, but still human is still the bottleneck. We cannot proceed, we cannot add until a human actually makes a decision, and it's still human will get a lot more to label it than what they can handle it. So
I guess what I'm getting at is I would expect that the active learning to be much more effective if it is able to make its second decision based on knowing the results first, right? So what you described earlier for how it decides what to choose next for labeling
Right.
is very much based on this is my current model. This is this very narrow edge. I want to choose stuff along the edge.
Right.
If it chooses a bunch of stuff along that edge, and it gets back the first few results and says, oh, I learned something. The edge is actually over here. And all of a sudden, all the stuff it chose earlier is no longer relevant.
Right.
It's going to perform a lot worse if it has to make all its choices up front without seeing the results.
Yeah, that is actually, there is some area called active class labeling, I believe, if I don't, the exact terminology behind it, but that's exactly to focus on that area to have the reverse loop rather than always select the samples, then the learner picks the samples, then give it to the human rather than having the other way too. I think there's a area on that, but I haven't actually experimented that particular. It's called, I believe it's called active class labeling, or it's not active class something. I forgot the name. Full. Huh? No. There are actually the active learning initially started with the just label being the key primary initiator, but later on it changed into active feature engineering and after feature selection. So one is about label, other one is feature. What are the features we should select and give it to the human? It's the active feature selection. And the other one is about the one you are talking about is active class. I forgot the final word for it, but I look it up and get back to you on that one. But yeah, there are several active variants which tackle different problem cases.
What you're doing, what are you closer to? Are you making most of the choices up front and then getting the results, or are you doing a portion of it and getting results and requesting another portion?
Mostly because we have actually, we already have a good enough model. So we want to now to improve it, what other ones which we are missing, which if we give it to the human to annotate it and re-add it, it will improve our performance. So we are doing
all the choices
up front, exactly. Yes, yeah. Because we already have a good model, we want to just get better at it. So, yeah. Right. So basically for this one, the criteria used is KL divergence, which is actually a way to basically compute the difference between two probability distributions. There are several ways to compute the criteria. The Shannon divergence, that's also another way. So several criteria. The one I used is the KL divergence, is popular used to as a criteria for determining the consensus. No, I just wanted to try with the simple one first to make sure that are we getting anything promising with active learning in general, right? So then explore more on the criteria, whether one criteria yields better than that. I think even with using the basic KL divergence, you see that there is a slight lift in performance. So I think so. Categories?
Yeah, categories.
Right.
How do you do that?
Yeah, so actually we use, first of all, H2O is really good. H2O handles a configurable number of categories. So if you use the H2O platform, so the default is 1024 up to, you don't see a value more than 1,000 categories actually. Typically, we don't have, most fraud cases, some of the largest I have seen about 700, 800 categories. But even if it's more than 1,000 categories for your different application, it's a configurable value in H2O. What they do is actually they use some kind of binning. To if there are more than X number of categories, they bin several of those categories into a bigger bucket. So that's typically the way to, for continuous variables, the only way is to do a binning. Right? Similarly, for categorical variables, a large number of categories, you bin some of those categories into a one bucket. Or not few buckets.
Swap, and it doesn't have feature for you to bin the
Yeah, actually H2O has that feature. If it is greater than 1024, it will automatically bin it for you. That's configurable, but that you can change it as well. Anything else?
So, what was your motivation to use multi-layer network neural network model versus semi-supervised learning SVM? I mean, have you done any work on that to compare their?
Yeah. So it's mainly that we have shown our models have shown that incredible performance. The neural network is working very well for us for quite a bit of time. But we have reached a saturation point. So given that we have our earlier models are neural network based, obviously feed-forward neural network with more layers is probably the next logical step to see whether we are getting improvement performance. We don't have.
The point I'm saying, I don't know how your actual posterior process is span out, but what I'm getting to is like when you cannot parallelly train a neural network model to get accurate parameters versus you can train other techniques like SVM and
Yeah, neural networks works very well actually. I mean, we have a lot of expertise in actually fine tuning to get the neural network. Well, most of our models are neural network based.
how much time does it take you to train large language models?
So with the current, it's like for example, with H2O, anywhere from few hours to sometimes it's days. So some of the models it runs for a week or so to train. All right. Okay, that's it. Thank you very much.